Okay, so welcome back to another lecture in the series of microprocessor systems design and interfacing course. So the last lecture was all about the architecture of ARM Cortex M0 Plus. I hope all of you watched that and understood what is inside the processor core. Of course, we had a detailed discussion on the register map about the 13 registers with the 3 special registers, what is the role, all those things we discussed. We also discussed about the memory map for the Cortex M0 Plus device. Even though memory is not part of the processor core, we all know that a microcontroller system or a microprocessor system is rather a memory driven system, right? So everything appears to be like a memory location for the microprocessor. So we did discuss about that in some detail about the memory map, and I hope everyone is thorough with that. And in this lecture, this week rather, we are focusing more on the programming side. Okay, so particularly on the assembly language programming side. So we will start with how the programming is to be done. So I'll briefly introduce the board that we are going to use for this course as well, and then of course we will dig deep into the instruction set of Cortex M0 Plus. There are around 56 instructions, but we are not going to discuss in detail about each and every of them because that will be utterly boring. So what I suggest is actually you do play with them, all these instructions. Always refer to the reference manual of ARM Cortex M0 Plus. In the lab we will introduce you to the software that we are going to play with, which is Keil Microvision. So all those things are going to be introduced this week. So take it slowly, understand it very thoroughly, and this will help you in a long run. Okay, so let's actually start with, I just briefly introduce the board that we are going to use for this course. So I briefly mentioned about this. So this is manufactured by NXP Semiconductors. They licensed the Cortex M0 Plus and the peripheral IPs from ARM and manufactured this beautiful Freedom board. The full name is Keil 25Z Freedom board. There is a lot of, so you can actually search around it. So rather than I introduce each and everything of this, you can search around it and get the reference manual and understand what all things are there inside. But on a very high level, I will tell you what all are there. So you do have the Cortex M0 Plus processor, which is actually sitting right here, which is the name is Kinetis L series. So inside of it will be the Cortex M0 Plus processor. And you do have 128 KB of memory map, which we discussed right in the previous session. If you go back and see the code part, you will see that it's 128 KB. Totally this can support around 4 GB, which is supported by Cortex M0 Plus. And on the peripheral side, if you see, there is a debugging option which is actually shown here. So serial debug access, it's what mean by OpenSDA. So there is a definite interesting aspect. There is another microcontroller which is to control the serial debugging access. Okay, so that's the major part. And then of course there is a coin cell. You can actually use the coin cell to operate this board. You don't need to actually power it from external side. If you want to power it from external side, you will use the USB power. Okay, so that's the way. There is no explicit power supply or power code for this board, but it is through the USB powering. And then of course peripherals are very interesting. You do have a PWM controlled LED, which is a tricolor LED, which you will be using in one of the labs, in the coming labs. You do have an inertial sensor, accelerometer gyroscope combination, which is actually there built in for you. And then there is a touch sensor also. Okay, so capacitive touch sensor also, which is actually shown over here. So if you go to the board side, so this is the Cortex M0 Plus core. The touch interface is here, and then you can find out the accelerometer. Right? In fact, I think there is no gyroscope. It is just 3-axis accelerometer, which is actually found over here. And all the other, this is the other controller, which is for the debug option, the SDA debug option, which is through this. Yeah, so other peripherals, please have a look at the board which for more understanding of it. But anyway, you will be using them, some of them in the coming experiments and the coming lectures will be dealing with them. But this is a board, it's just 1500 rupees board as of 2018-19. It might be lower by now, but if you are very keen feel free to purchase. This is a very powerful board because the specifications we already saw in the last lecture, the power of this Cortex M0 Plus. So please go ahead and buy this and keep it with you, because you can experiment then freely. And in fact, we will give to you when you come to the lab next week, so you can take it to the hostel, play with it. Okay, experiments will also help, and then later on you can be on your own. Okay, so experiment with the board and learn it thoroughly. So going forward, so very important to know what happens when you switch on this board or when you reset this board, what exactly is happening inside. We had a brief mentioning of this from a programming flowchart perspective in the last lecture, but this is again a revisit of that in a slightly higher level. So it's something like this, the overall. So I shaded off, in fact this is from the reference book, textbook, so you can always refer to the textbook and get more details, but we will briefly touch upon it here. So what is happening here is I shaded the portion which is not happening at the start. At the start, what is going to happen is you press the reset button or you press the power on button, it will go to the reset option, and then in some cases, not all cases, there will be a bootloader. Okay, so this is optional. So some microcontroller designers want some boot loading, just like the BIOS that we have in our computer. Some prior things have to be done. So till that time you have no control. Microprocessor also have no control. It's something which is priorly defined operation. So it's optional. Our case, we may not be using this at all. Okay, so that's it. And then of course there is a reset handler. So this is like a location in memory. It's like an address in memory where you will put the code you want to execute. Okay, so that's the case. So certain things actually happen. For example, in the reset handler itself, the first line of code is to initialize the system. It is like clearing off the registers or doing some initial settings. So it is again optional, but I will give you an example, okay, for this particular thing. So that's some system initialization will happen. It's optional. You can disable it or you can enable it. So that will be the immediate thing which will be at the reset handler, and after that it goes to the startup code. That's what actually mentioned here. So this is the first few things which is happening when you reset, when you press the reset button or when you switch on the system. And once this is done, you will have the startup code, and that is where you will write maybe your main code or whatever interrupt routine. Everything will be actually sort of could be called from this C startup code. So this is a fixed one given by the designer. So I will show you again this thing in the actual Keil Microvision software. Where is it happening, all these things with a sample code. Okay, so that's the thing. And then of course the last part is, after all this is done, the control is given to the main program where you can do some processing, you can do your own code, you can do the interrupt service routines, and lot of runtime libraries you will be using. For example, you can work on neural networks and there is a built-in neural network library for you. Okay, so that's the thing. So basically this is the sort of a sequence that is happening. No need to by heart, please don't take in that sense. You just need to understand the flow, that's it. And I will demo this for you through an example. Okay, so that's the scenario here. And then what is really happening is, okay, let me actually demo this part, okay, using a sample code. So you may not be understanding that code at all, you can safely ignore it. All I want to show you is basically how the code is going to run. Okay, so let's do that. Okay, so this is the Keil Microvision software. All these things you can ignore. There will be a separate session where the Keil Microvision software will be introduced to you and you will be doing it hands-on. Okay, so basically we will run this. I will just debug this circuit for you, and we will again explain what all these steps again in the lab, so you don't have to worry everything. But this is what I wanted to show you. So in the slide we actually saw that it is the bootloader is optional. We don't have this in our case. We do have the reset handler, and that is exactly happening. So I'm inside. The moment I run the code, I'm inside the reset handler, and all you can ignore all these. All these are some things which we will discuss very soon, okay, in the subsequent slide. But if you see over here, the interesting aspect is it is in the reset handler, and then the first step it is going to do is it is going to mask all the interrupts. That is because when you are going to initialize the system, we are going to initialize the system here. So at that point you want no interrupts, which is user defined interrupts, to get activated. Okay, so that's the concept. So interrupt, when you study when you discuss about interrupt, we do have a separate session about interrupts. That time you will understand what is this maskable interrupt and what is this non-maskable interrupt. But just to give you a feel, The non-maskable interrupt are something like critical interrupts or critical things that you want to execute. For example, the temperature got increased and you want to shut down the system. That cannot be postponed, right? It has to be immediate. So those things cannot be masked. But there are certain interrupts which are user-defined interrupts which can be masked. So those are masked. Okay, so that's the thing. Let me actually run it through. So then you go and do the system initialization. So this is the assembly code. I have not introduced the instruction set to you, so you'll be wondering what is it. So let it be vague to you. You don't know anything, but what I can tell you is that this is the initialization. So I'm just going through it. So this is the initialization code. In fact, this is written in C. So you can see, actually you can write your code in C, or you can write your code in assembly language, and you can write a mix of it. It doesn't matter. So that is a beauty. Okay, so the initialization, we don't worry about this at this point, but again this we will revisit. Okay, so don't worry, just like all the lectures so far, we'll keep on revisiting many things, because there's not an order. I can't teach it in an order because it's a system. So some things you will learn first and then you come back. Okay, so at this point you can think that this is some initialization. So let me just quickly skip it through. And after the initialization, you are again enabling the interrupt. Okay, all the interrupts are written, and then this is very important. So you have a main function. So the name is actually double underscore main. So you can't change it. If you want to change it, you have to change the name here. Okay, and then I'll go to that main code. So this is a main code for you, something which I have written in the assembly code. So this is it. So the same step. So we didn't have this bootloader option, but we did the reset handler where we did the system initialization. Then the startup code is nothing but what you are actually gone through, and then you are in the main file. So that's the meaning of it. So I hope it's pretty clear. Okay, so coming back, let me just make it full screen again. Okay, so what is a typical program generation flow? So I might have written a program in C or assembly language, and then I already showed you the debug, but there is a build option also where I build the code and then I can run the code on the hardware. So what is that typical program flow? So this is the typical program flow. Okay, so let me actually explain to you. So you can write your source code in C or in assembly. Okay, so up to us. We will start all our experiments in assembly, and towards the end we will show you how you can write C code, because C code is very simple, easy to write. And if you start learning this, then you will be having no interest in coding in assembly. But there is a significant importance, because you don't get the same flexibility like you write in the assembly code when you write in the C code, because C code is very easy to write, but then the way it is getting compiled, it may not be optimized. Okay, so if you want to write a very optimized code, you have to write it in assembly. Okay, so very important. So let's say you wrote the code in C. So the moment you press the build button, what is going to happen is the C compiler will come into the picture, and it will create the .of file. We call it as the object file. If you have written it in the assembly language, it will be converted to the .of file, and then it will be going to the linker. The linker will be including all the libraries, whatever you wanted. For example, in the case of the C code, you might have included the standard input output.h, right? Some header files, some library functions. You might include some DSP functions, some signal processing functions, or you may include some neural network libraries. So everything will get linked. So your source object file will get linked with your library files, and then it will create an executable. So in the case of ARM, this is something in the format like .elf or .out, which is the common. Okay, so ELF is more for the simulation, and AXF is more for the debug option, and out is more for the programming option. Okay, so that's it. Moment you have that, you program the flash, and then you press the reset button, it will be executing whatever you written in this program. So this is the flow. Okay, so two things, two paths. You can write it in the C code, or you can write it in the assembly code, doesn't matter. The compiler or the assembler respectively will convert that to the object file, link with the libraries, and convert that to an executable image. So this is a very typical process that you see even in Windows or in Linux or in Mac operating system. You might have written something in C. The process is more or less similar. Only difference is the executable in the case of Windows will be a .bin file or .exe file, for example. In the case of Linux, it will be something else, and in the case of Mac, it will be something else. That's the only thing. So in our case, this is a flow, and everything will be written onto the flash memory. So flash memory, the advantage is like it will remain even if you switch on the switch off the system. The next time you switch on, it will go to the flash memory. It will go with the reset handler first, and then it will go to the flash memory and starts executing there. Okay, so that's the typical program flow. Okay, and the development flow is something like this. So you create a project, okay, then you select device and specify the project options. So very important, because we may be using, for example, you start with the Keil Microvision, you will be selecting a project, then you will be selecting the device and all those things, and then you add your program code, device, drivers, whatever library you want, everything will be added, and then you compile it. Basically press the build button, and then you, if you want to make any, so basically once you compile, you can download to flash, and then you can debug. If you make some thing, you again have to recompile. Very important. Okay, so this is a way. So you will be having an interface on your desktop or your laptop, which is actually Keil Microvision. Through that you will be connecting to the actual board. Okay, so this is the development flow. In fact, it's not restricted to our case. This is the way we work on in any modern day processors, okay, using any interface. So Keil Microvision is what we are using, but there are different options. You have the IAR workbench, for example. You have the GCC compilers, which you can directly use. You have embed systems, which are actually web-based interface, where you won't be able to do a lot of debugging. So, but you can definitely be able to burn your code onto the flash memory. You can use any of the softwares. But Keil Microvision, why we have go ahead with it is a very sophisticated software with good debug options, and that's the reason when you learn the system, it's very important that you debug it thoroughly so that you understand everything very clearly. Okay, so let's actually take this out, and I want to show you in the actual Keil Microvision how this is done. Okay, so let's actually go back again to the Keil Microvision software and come back. Okay, so I'm in the Keil Microvision. The moment you double click on the exe file, you'll end up in this page, and then the important thing is like you need to actually first of all select the you have to create from the project menu. You have to create a new project. So just give some name. So I've given already test one, test is already there, so I just give in some test one. Then it goes to this menu where you have to select the corresponding device. So for us it is NXP. So please follow the installation document that we have already shared with you. If not, we'll share it with you soon. So follow that, install the Keil Microvision software, install all the packages that is required. So if you have done that, when you come to this menu, you will have this option. So expand the NXP, expand the Keil XX series, then go to Keil 2X, and then our board will be listed here, Keil 25Z128. Okay, so that's the board. So some explanation of the board will be given here, and then you just press OK. So this screen will pop up, and in this also there are libraries. So basically what you have done, I just want to go back. You created a project, you select the device, and then specify the project options that we will do in the coming few pages, and then this is the important part, the device library. That's what we are going to do now. So if you expand here, there is an LED support which is not mandatory. You just see CMSIS. It is a standard protocol or standard software which is actually, or standard library or driver library which is available for us, and we will be using it. The reason is like there are certain startup code which is ready-made available to us. You don't need to write it from scratch. So that's the reason why we are going to use it. So the core only you select. The DSP and the NN, the neural network library, is for advanced applications. So if you want, you can actually use it maybe towards the end of this course. At this point only I'm interested in the core one, which is actually core to the Cortex M0. So you can see it, Cortex. In fact, this is common for all Cortex M series. Okay, and then I'm not going to have any operating system. Please remember that embedded systems may not have any operating system running. It is just bare metal flash where you download your program. But if you want to have a very controlled environment with a lot of autonomous things to happen, then you may have to have an RTOS, real-time operating system, running on it. So you can do that as well, but here we are going to go with bare metal setup, no operating system at all. Okay, so those are for advanced course. Okay, so there is a course on computer architecture, advanced computer architecture, where if you take that course, you may be learning all these real-time operating system related aspect. At this point, this very bare minimum thing that we need, which is the core. And then one more thing is like you can actually go through all these, but these are all for the peripheral interface. When we deal with that, we may have to load all these. Otherwise, go to device and then select the start. In fact, I think you may not require this core also, because we are not going to use the CMSIS way to start with. But yeah, for the making it a habit, you just select these two. That's all. Okay, so even embed option is also there. We are not going to use that. So this is another way to program your board. But what we are going to go with is the very bare minimum standard way. So you do that and then you click on this. That's it. So you will see the things here. So if you see this warning, you just right click and update. That's all. Okay, update, it will go. So what I'm saying is some cross here, right? So you just update it. Okay, and now you go here. You can create a new source if you want. So you just need to go to this and create a new source. C++ assembly language option is there. I will go with assembly. So I already created a file for you, so I will just load it instead of creating a new one. If you are creating it for the first time, you put a name here and just plus add, it will get added here. But I will add one it's already existing. So I'll just go here and select the ASM option here, and then the files, many of them will be loaded. So I'll just load one of them, which is already there. I think it's already coming. Yeah, this is it. So this is the assembly language I have already written. And what is all these things? You have not studied it. I will explain to you in a separate lecture, so don't worry about it. What the objective here is just to show you the program flow. Next is actually on the target. Next to it, you will see something here. This load option is to load the ASM built file. These things. If you go back to these files to the flash, that is this option, load option. But before that, let's actually set things. So this is this part, the project options part. Okay, so that's the thing I'm going to do. So a lot of options. Device, we already did it, but counter check everything is correct. If you made any mistake, you can most probably correct it here, but I won't advise that. Do it correctly at the first time. Then target, you can specify the ROM and RAM, or you can even use a custom file in the format. So you can do that, just like we used to do the memory mapping. You can redefine, but I suggest to go with whatever is default. Then the output part, you can create a hex file if you want, so that's a good option to choose. Okay, but create executable is very important. So this will be inside this folder. Debug, you can deselect or unselect if you want to have less information. Okay, so then this is not very useful for us. User is also, all these are advanced stuff, so we'll ignore all this. Okay, and then ASM also is the advanced, so you just ignore it. So you can use memory from the target dialog, which is actually from here. So select that. Other way is to create a load from a file. Sorry, ASM. So if you don't do this, this will be the SCT, this is a scattering file where you can define, but that's all for advanced, as I said, so don't do that. Just select from the target whatever you defined here. Okay, and then go to debug. Here it's very important, please don't forget to do this. So the right hand side is for the actual board. To start with, we are not going to use the actual board, but we will be using simulator. So you can go to select use simulator, that's all you need. And then that's it. Utilities, everything is fine. You don't need anything to set. So after that, you press OK. You go to project. You have the build option here. Just press build, and you can see there is no error. There will be some warning which you can ignore because those are some minor things on the memory layout part. Okay, so you can ignore it. Warning is fine. Oh, sorry. Okay, so you built it. Now what we need to do is, you can actually, if you had the board, if this is simulation, so this load doesn't make any sense, what we are going to do is we will do the debug. So you press on the debug button. Okay, the moment you press on the debug button, it goes back to what we were showing you in the earlier stage, and then you can actually press this option that is shown here. Okay, so this particular thing, you keep on pressing, it will go step by step. So that's it. So other things we will discuss it at the next stage. So this is the entire step that we discussed. So we did the debug, and that's a entire thing. Okay, so coming back here, so assembly, is the language that we are going to start with. Okay, so very important. And here is a very interesting slide. This side I love it because this is the evolution that we had over years. Okay, so when I was doing my BTech, we used to code everything in 8051. So we had a very big interface board, and it's like it occupied almost like the size of a laptop. And then the coding was all 8-bit, so you need to have tons and tons of instructions to execute something. Okay, so some instruction I'm doing over here, it doesn't matter what is it at this point, but the time is something like it took 48 clock cycles, and the memory was like 48 bytes. Doesn't appear to be huge, but yeah, there's a lot of coding. Then 16-bit example, the same functionality. If I used 16-bit instructions, it used to be like this. You can see the number of codes getting reduced drastically, and the number of clock cycles, obviously you don't need those many, right? And then of course the memory also got reduced. Okay, and then in the Cortex M, this is, now you know what is it doing. It is just doing multiplication. R0 is equal to R1 into R0, that's the meaning. Just need one clock cycle if there is a hardware multiplier. If it is used, it is just one clock cycle, otherwise it takes 32 clock cycles, and the memory is just 2 bytes. So this is why we are so loving the ARM Cortex M0 Plus, and that's the reason why I chosen, because even now some colleges follow 8051, but I seriously feel that you're going to be handicapped if you're learning that, because if you learn Cortex M, you are almost industry ready and you can start doing some exciting projects with this. Okay, so that's the reason why we chosen this, even though it's a bit tough, many of the concepts to get introduced to, but it takes some time for you to get used to. After that, you are all set to get ready with doing some exciting projects. Okay, so just before we wind up, just before we go to the instruction set, couple of slides before we wind up this particular lecture. One is on the Keil Microcontroller Development Kit, the Microvision software. So it is a full development kit which is given to us by ARM, and for IIT Palakkad it is actually the professional version is also free. They given to us as part of the ARM University program. So what it is actually is, there's a lot of things which is made easier for you. You don't need to actually think about the compiler. It is all there for you. Otherwise you may have to use, if somebody is going to do it on Linux, you can do it, but the debugging is a very difficult task there, and you may have to use the GCC compiler to convert the C code or the C code to the object file, and you may not be able to do it a very efficient way. So we go ahead with the ARM. They do provide us the compiler. There is this Microvision software I just showed you. It has a very beautiful GUI. It's a good editor and a very good debugging option, so you can do that. There is RTOS option also, which we will not be studying in this course, but if you are passionate about it, there's a lot of materials available where you can extend the understanding that you get from this course to the RTOS. Okay, so you can do that. And then of course there is a lot of debugging option. We are going to use this Ulink 2 and Ulink Pro debug option. Okay, so but don't there's no need to understand them in depth again for an advanced stuff, but this is the debugging way, debugging software hardware interface that we are going to make use of in our labs, for example, or in our further experiments, for example. Okay, so but you don't need to understand what is it. For us, it all is sort of abstracted in this software. So we just need to know how to use this software, how to write beautiful assembly programs, beautiful C programs. Rest is taken care of in this MDK. Okay, you don't need to actually understand everything. But overall, just wanted to give a take-home message that there is this beautiful microcontroller development kit which we will be using, okay, for all our purposes. And then before I dig deep into the ARM Cortex M0 Plus, I think I will stop this lecture here. Okay, so next lecture we will start talking about the ARM Cortex M0 Plus assembly, the instruction set, the richness of it, how to write the programs, all these things we will be talking in this week. So this week will be fun actually, because I hope every one of you, each one of you will install the Keil software on your system. If you have a Linux or Mac system, I suggest you to actually have a Windows virtual environment and install this in there, okay? Or you can actually try out on the lab system if you really don't have it, but I suggest you install in your laptop because you do have that flexibility then to work from anywhere, right? So you do that and start enjoy this lecture because it's all hands on. You can always, that is the advantage of being an online session, because in classroom session maybe it's slightly difficult for me to switch between the Keil microvision and the slides, but giving an online video it's very easy. So I'll do that. You can also pause the video and try to do it yourself. Okay, so please do that, and I will stop this lecture for the moment and we'll come back with the subsequent lectures. We will have short crisp lectures this week, and highly encourage you to try it out. Okay, so don't just watch it, just try it out. Okay, so thank you, see you in the next lecture.